Hello dear all students. Today we are going to discuss about the first law of thermodynamics, which is an extension of law of conservation of energy principle, which is adopted for the thermodynamic processes, different thermodynamic system that distinguish the two kinds of transfer of energy as heat and work and relating them to the function of body states. So let us start with our today's session. The concept of mechanical equivalent of heat. The mechanical equivalent of heat is given by the James Prescott Joule. He demonstrated that the water can be heated by doing a mechanical work and showed that for every 4186 joule of work done, the temperature of water raised by a 1 degree Celsius per kg. So let us see how Joule's experiment is. So this is the actual experimental setup used by the Joule, in which he used one insulated container having the water. Inside that container there is one shaft to which the number of rotors or paddle wheel is attached. To the end of the shaft there is one spindle, and to that spindle the two pulleys are attached with the help of rope, and to the end of this rope there are the two weights, equal weight are attached. Again, this spindle can be rotated with the help of this rotating wheel, and due to the rotation of this wheel, the weight attached to this rope can be fall or rise over the pulley, right? And due to this, spindle shaft inside the container starts rotating, and rotors attached to the shaft also starts rotating. Now here in this case, due to the rise and fall of the weight over the pulley, means this weight possesses the potential energy, means the potential energy of this weight is first converted into the kinetic energy, right? And this kinetic energy utilized to rotate the rotor, means here the kinetic energy is converted into the mechanical energy, and this mechanical energy is utilized to raise the temperature of water, which is recorded by this thermometer. So this is how this Joule's experiment perform. Now Joule's experiment, in this experiment the work input to the paddle wheel is measured by the fall of weight or rise of the weight corresponding to the temperature rise of the liquid, right? And in the insulated container it is measured with the help of this thermometer. And this experiment shows that a definite quantity of work required to accomplish the temperature rise obtained within a unit amount of heat, right? And regardless of whether the temperature of liquid is raised by a work transfer or heat transfer, the liquid can be returned to its identical state by heat transfer in opposite direction. Means when this insulation is removed, then the water can be reversed to its identical state by the in opposite direction because of the heat transfer from system to its surrounding, right? So from this result we can say that heat and work are the form of energy, and this is how Joule's perform his experiment and proved that the for the 4186 joule of work done, there will be a rise in the temperature of water through 1 degree Celsius. So from this Joule's experiment, we can say that when a system undergoes a thermodynamic cycle, then the net heat supplied to a system from the surrounding is equal to the net work done by a system on its surrounding. So we can write cyclic integral of dq is equal to cyclic integral of dw. First law of thermodynamics cannot be proved analytically, but experimental evidence like the Joule's experiment has repeatedly confirmed its validity. Since no phenomenon contradicts to it, so it is accepted as a law of nature. First law of thermodynamics applicable for the both reversible as well as irreversible process. It can also be stated as heat and works are mutually convertible, but since energy can neither be created nor destroyed, the total energy associated with the energy conversion remains constant. So we can write cyclic integral of dq is equal to j into cyclic integral of dw, where this j is nothing but the proportionality constant, or also known as the mechanical equivalent of heat. So this is how. What about the Joule's experiment? First law of thermodynamics. As we know that first law of thermodynamics is an extension of law of conservation of energy, which states that the change in internal energy of system is equal to the difference between heat added to the system and work done by the system. So according to this statement, let us consider U1 be the initial internal energy of system, Q is the amount of energy supplied to the system, W amount of work done, and U2 be the final internal energy. So according to the statement, change in internal energy, that is U2 minus U1, is equal to the difference between heat added Q and the work done by the system, that is W. So this is what we can write from this statement, delta U is equal to Q minus W. Now, generally, when the heat is added to the system, here in this case, heat is added to the system, its temperature rises, right? And external work is performed due to the increase in volume of the system. And the rise in its temperature is an indication of increasing the internal energy of the system. When we add the heat to the system, there will be a rising temperature of the system, and due to the increasing temperature there will be a increase in internal energy of the system with the expenditure of useful work. Now when the heat is transferred from this system, now when the heat is transferred from the system means there will be a decrease in the temperature of the system, and the internal energy of the system also decreases. In that case, the work is to be done on the system. So this is what about the first law of thermodynamics. Energy, a property of system. Consider a system which changes its state from state 1 to state 2 by following the path L, and return from state 2 to state 1 by following the path M. Now here is one system which changes state from state 1 to state 2 by following path L, and return to state 1 by following path M. So this complete system execute one complete cycle 1 to L, L to 2, 2 to M, and M to 1. So writing the first law for the path L, we can write QL is equal to delta EL plus WL. Let us give equation number 1. Writing the first law for the path M, again QM is equal to delta EM, that is change in internal energy, plus WM, that is the work done during the path M. Let us give the equation number 2. The process EL and M together constitute one complete cycle, for which we can write the cyclic integral of dq is equal to cyclic integral of dw, right? So ql plus qm is equal to wl plus wm. Hence ql minus wl by shifting the wl to the left hand side and by shifting this qm to the right hand side. So from equation 1, 2 and 3 we can write delta EL is equal to minus of delta EM. Let us give the equation number 4. Now let us consider again, when the system returns from state 2 to state 1 by following the path M instead of N path M. So we can write directly delta EL is equal to minus of delta EN. So from equation 4 and 5, delta EM, change in internal energy during the path M, is equal to the change in internal energy during the path N. So we can say that change in internal energy between the two states of a system is same whatever the path the system may follow in undergoing that change of state. Therefore, energy has definite value for the every state of system, and hence it is a point function and property of system. So this is how we can prove that energy is nothing but the property of system. Let us see some numerical based on the first law of thermodynamics. 2000 joule of heat is added to a system and 2500 joule of work is done on the system. What is the change in internal energy of the system? Now, here in this case, let us consider a system here in which the heat is added to the system, that is 2000 joule, and work is done on the system, that is 2500 joule, and we have to find out the change in internal energy of the system. So given data, heat Q is equal to 2000 joule as heat is added, so heat added to the system is always taken as positive. W is equal to minus 2500 joule as the work is done on the system, that's why it is negative. You have to find out the change in internal energy, that is delta U. So according to the first law of thermodynamics, we have delta U is equal to Q minus W. So by substituting the values, we'll get the answer as delta U is equal to 4500 joule. So this is some basic numerical. Let us see one another. In cyclic process, heat transfer R plus 14.7 minus 25.2 kilojoule minus 3.56 kilojoule and plus 31.5 kilojoule. What is the net work for the cyclic process? So this is actually the cyclic process in which the number of heat transfer are there, right? Positive sign indicate the work heat is supplied to the system, whereas negative sign indicate the heat is rejected from the system. So summation of all the heat transfer, that is equal to 17.44 kilojoule. So from the first law of thermodynamics for cyclic process, we can write the summation of Q is equal to summation of W. So W is nothing but equal to the Q, that is 17.44 kilojoule. Example number 3. In an air motor cylinder, the compressed air has an internal energy of 450 kilojoule per kg. At the beginning of expansion, the internal energy of 220 kilojoule per kg. After expansion, and if the work done by the air during the expansion is 120 kilojoule per kg, calculate the heat flow to and from the cylinder. So let us first write the given data. Here at the beginning of expansion, internal energy is 450 kilojoule per kg, right? And after expansion, U2 is nothing but 220 kilojoule per kg. Work done by the air, means this is nothing but the work done by the system, that's why W is equal to positive. We have to find out the heat flow, that is Q. So according to the first law, we have Q is equal to delta U plus W, right? So Q is equal to, by substituting the value of delta D, that is the U2 minus U1 plus W. So we'll get the answer that Q is equal to minus 110 kilojoule per kg. I hope you have understand the concept of mechanical equivalent of heat, first law of thermodynamics, and energy is a property of system. So thank you for watching this video.